So I'm here to talk about the new ZKsync announcements, which is two of them together combined, ZKsync Airbender and ZKsync OS. I'll get to more details, but basically ZKsync Airbender is a new RISC-V zkVM proof system, and ZKOS is sort of a wrapper layer on top that I'll talk about soon. So about me, I work as DevRel at Matter Labs, one of the core teams at ZKsync. I like math, and yeah, recently we just open sourced Airbender, which if you've been following really closely, you'll have heard about Boojum 2. That's the same thing. We just renamed it just recently because Airbender sounds way cooler. It gets the name Airbender, by the way, because it is Stark-based and uses AAR constraints, and so it just sounds cool. So there we are. So yay, another zkVM. We're up to 25 or something now. So I'll explain kind of a little bit why we chose to build our own again. I mentioned earlier in a panel, partly it's because we're paranoid about using other projects' code. But yeah, I want to start actually with ZKOS because it's going to make more sense going backwards. So what is ZKOS? Even before that, I'm going to start with Boojum, which is the current proof system. So why are we moving on from Boojum at all? On the right, it's not really meant to be visible, but that is an architecture diagram of how Boojum fits together. My point in showing this to you is that it's kind of complicated, and it's actually like a very tightly conjoined mess where at the very top, there's a main VM circuit, kind of, and everything flows through that into this complicated process of follow-up circuits, which we learned was very difficult to make any updates to, make any upgrades with. And furthermore, this never really gets talked about that much, but we build the proof system and all the constraints kind of in one repository. And then separately, we also had to keep track of a different virtual machine just for the sequencer to run. And so we're running like two full virtual machine code bases. One of them for the sequencer, which needs to be fast and have a lot of like optimizations there. One of them for the prover, which is optimized in a totally different way. And the prover code, if you change like one thing, you also have to update probably these other 16 different places. So yeah, this is why we're moving on. With ZKsync OS, what this is sort of a wrapper layer around the proof system, or like above the proof system. So the proof system is going to come underneath, and what ZKsync OS will do is let us use multiple execution environments. We can have one VM implementation, and then you can just compile that to x86, like your hardware that you're running it on for the sequencer. And then when it comes time to prove, you take the exact same code, almost, I'll explain, and you just prove that, compile it to RISC-V, and now you know the like at least hopefully like your sequencer or prover are mostly doing the same thing. There are like a couple small differences of things that need to happen in the prover, but not the sequencer. But those are much easier to keep track of this way, as opposed to having two wholly separate instances. So I think that was actually one of the biggest motivations for us, was just every single like upgrade to the VM or upgrade to ZKsync was a big pain with Boojum, and it was really hard to even get stuff like precompiles that we needed for like ZK verification. And so this is why ZKOS is going to save us forever. Even if we swap out ZKsync Airbender in the future, like the proof system underneath, OS will still work as sort of like an operating system layer, and it'll hide everything. It's also faster and cheaper, which is great. Specifically, it's a state transition function implementation that enables multiple execution environments within a unified system. These pictures will make that a little more clear. It kind of comes into three parts: the bootloader, the execution environment, and the system, which here is a breakdown of processing one L2 transaction, or you could do a series of L2 transactions. The main stuff's happening in the middle. Focus on the bootloader first, where you see there's that TX processing box. We parse a new transaction as it comes in. We're going to calculate some resources like gas usage. We'll validate the transaction's valid, the signature's valid. And then we actually execute the transaction. And then if you need to do sort of refund or cleanup work at the end, that's how that part works. On the left-hand side with the system, you can see that we're reading data, read-writing data, and writing data. System is where we sort of like abstract away all the hardware. So the system is what's kind of hiding whether you're actually on like an Intel chip or a GPU, or you're not even like worried about the hardware because we're doing like RISC-V and we're proving it. So the system kind of hides the hardware part, and then the execution environment is just like completely swappable out. So it's even designed to the point where, partly because we have historical era VM and we're trying to prove EVM now, you could, like within the same smart contract, start in an EVM execution environment and call to an era VM contract, and this code will like properly separate each execution context, which is very nice. So even theoretically within the same blockchain, you could have like an EVM smart contract, a Wasm smart contract, and they could kind of talk to each other this way. So ZKOS, I expect to stick around pretty much forever for ZKsync, at least for the foreseeable future. And then ZKsync Airbender is our new proof system, which is designed specifically to prove this, but that could be swapped out later. So, all right, the main pitch for Airbender, if you remember one thing, is that we are trying to prove ZKsync mini blocks in 1 second. This is like our whole focus with the proof system is we want 1 second proofs. Every single second, we want to generate what's happening on ZKsync. And the reason we're doing this is because we're going to use it for interoperability. I won't talk too much about interoperability today because we're here at Ethproofs. We're trying to prove things, but 1 second is our big target. So boring facts, I'll read them off. It's RISC-V, 32IM instruction set, deep Stark, Fry proofs, AIR arithmetization, Mersenne 31 prime, precompiles for Blake 2s, and U256 operations because the EVM's all 256-bit integers, lookup tables, recursion, memory argument. All right, there's your, take your screenshot. Nice. We have surprisingly good documentation for this repo, which is impressive if you have seen any of our previous code bases. I just took some like quick screenshots, and like all over the place, there are these huge lengthy essays, and even within each like section of code, there's pretty good documentation on like what variables mean. It's much more readable and like, yeah, so good job to the engineers who have documented a lot of stuff. If you have questions, like check out the actual code. I want to go over some of the facts that I find kind of the most fun about Airbender, which is, yeah, generating proofs of L2 mini blocks in under 1 second. This is the base layer proofs. So what that means is we are counting witness generation time, like the execution time, witness generation time, and like creating the first Fry proof, but we're not doing any of the aggregation layer yet. But that Fry proof can be good enough to like prove that 1 second's worth of transactions. And you can start using that for either pre-confirmations or interoperability. And so even without doing like a, you know, aggregating a bunch of these things together into one final snarked like Ethereum proof, one snarked proof that gets posted to Ethereum, you can still do a lot of this. At-home proving is possible, which we're pretty excited about. So there are two crazy people at Matter Labs who are very infatuated with GPUs, and they are actually running ZKsync blocks at home on single GPUs. Instead of 1 second, it takes them like 40 to 50 seconds if they're just using a single GPU. But that's like relatively reasonable. And if you just had like 40 or 50 people around the world, they could like all kind of keep up with the chain from home, which is pretty sweet. And then another interesting fact, kind of in a different direction, is I kind of lied earlier, actually, when I said that we have the RISC-V 32IM instruction set. We actually implement 3 instruction sets so far. We have the full one that we use normally because we need to prove like all RISC-V stuff. But we have these like reduced instruction sets that we actually use throughout the recursion layers, because when we're proving like recursively, we kind of know like exactly the format of what's coming in. And so we don't need to like be able to prove anything in the world. We need to prove something very specific. And so we actually can like reduce the number of instructions that we even need. Specifically, we can take out like signed multiplication, signed division. And that may not seem like it makes a huge difference, but when we're cutting it close already on like trying to fit things into like one hardware, like one piece of GPU, this can like make the difference into like fitting in one GPU versus having to chunk and like split across multiple things. And so, yeah, we have 3 instruction sets, which is pretty cool. And I haven't seen many other projects talk about this. I don't know how many other projects have multiple instruction sets or like kind of variations within. I think a lot of people are just kind of like cramming everything through the same thing. And maybe this is like a missed area for like cool optimizations. Okay, 2 more fun facts. We are 100% open source, including GPU. And yeah, since we always prove ZKsync OS, we'll have nicely formatted data so the proofs can be generated more easily. This is like a clunky sentence that I wrote for a PowerPoint slide, but in the code base, like when I was checking it out, some of the coolest optimizations are stuff where you can assume that data is going to be passed in like exactly this format, or that memory will be aligned like exactly in this way, because we are always assuming that we're proving like with ZKOS. So if you were to take Airbender and go use it for like arbitrary RISC-V program that is just like something else from the internet, you might have to be like a little more careful with like using a reduced instruction set. But if we know that we're proving ZKOS, like all of this works very nicely. Cool. All right, just about done. Some things to look forward to in the future are, I think this week or next week, we will have many more announcements about interoperability for the Elastic Chain. It's kind of what the 1-second proofs are for. And I will be resuming my every line of code of every zkVM series, starting with Airbender soon. So that's all. Thank you.